So all objects fall at the same rate if we ignore air resistance. It seems counterintuitive, but it is true. So if we have 100 newtons, and if we have 1 Newton, they will accelerate at the same rate. Right? And this is a really easy proof. Okay, what is the force on something? The force on something is its mass times its acceleration. What also is the specific force pulling something down? Well, it is the weight of the object. So the mass times acceleration of something is its weight, which is mass times gravity. Obviously, it's the same mass in both of these cases. So what is the acceleration that is pulling it down? In both of these cases, it's acceleration due to gravity, which obviously is a constant at 9.8 meters per second squared. Right? So everything will fall at the same rate, and you saw that in that video, the hammer and feather on the moon. Okay. With air resistance, it's obviously more complicated. Okay, so what affects air resistance? So what I'm going to do is I'm going to write up a formula which is actually not on the syllabus. Okay, I will make a note of this. The formula is not A-level. But I want to introduce it this way because, one, I think it's interesting to see what this is, particularly if you do like challenge questions, and also I think it nicely illustrates all the different factors that you do need to know. So you need to know the factors. You don't need to know this formula. Okay, so this is the drag force or air resistance. Okay, what's it affected by? Some constant, which we don't care about. This here is the density of the fluid. What is a fluid? A fluid is a liquid or gas. So that's kind of obvious, right? If you try and run through air, there's not that much air resistance. If you try and run through water, which is more dense, obviously there is more resistance. If you try and run through honey, right, as well as getting very sticky, you're going to find it's even harder. There's far more drag on you because the honey is denser. V is the velocity. So the higher the velocity, the more air resistance, which is kind of obvious, but you'll see it's actually proportional to V squared. So if you double the velocity, air resistance increases by 4. If you triple the velocity, air resistance increases by 9. Right, and that is a really useful fact to remember, because it does start to explain why it's so much harder to go faster if you're cycling, if you're running, if you're driving, right? Because the faster you go, the more air resistance increases, but disproportionately to your velocity. A is the surface area, which we all know intuitively. And then CD here is a drag coefficient, which you don't really need to worry too much about, its name or exactly what it means, but it's basically to do with the shape. Okay, and you all know that shape obviously has a massive impact. Okay, so something like a sphere will have quite a high drag. Something like a cube will have an even higher drag. Something that is streamlined, like this, will have a really, really low drag. All right. Now, the actual numbers depend on a lot of things, right? If you have a long cylinder compared to a cube, it will lower it for loads of reasons, which we don't need to go into. But these are just the sorts of things that will impact it. So how can we actually use air resistance in calculations or drag? So this is a little bit more simple than this formula, okay? We will have some object moving with some velocity, and there will be a force of air resistance. So let's put thrust here. So it's really easy, okay? We would do something like the thrust minus the air resistance equals mass times acceleration, just like we were looking at last lesson. So T minus R is ma, and then acceleration would be the resultant force over the mass, just like we were doing last lesson. Okay, so it is relatively simple for us to calculate. Obviously, if there is no resultant force, the acceleration is 0. If there is a resultant force, the acceleration is non-zero. So if the air resistance is greater, then the acceleration is negative, which means it slows down. If the thrust is greater than the air resistance, then the object would accelerate. A typical question will also be something like, what happens to the acceleration as we increase the velocity if we do care about air resistance? So what this is saying is we've got some object which is starting at 0, it's accelerating. What will the acceleration be if there was a constant force? Okay, so what's going to happen? Well, initially there will obviously be a large acceleration, but then air resistance increases, so the acceleration decreases a bit, and the acceleration will keep on decreasing until it reaches, I've done it completely wrong, ignore that. There will be a large acceleration, and the acceleration will decrease until we get to a value of 0. So it's the red one. Okay, so this means that the resistance is getting bigger and bigger and bigger, and eventually there'll be 0 net force, so the acceleration drops to 0. Are there any questions at this point? So a really common example of this which they do to slightly try and confuse you, is they'll give you like a measuring cylinder and they'll fill it full of liquid of some kind. Could be oil, could be water, and then they will drop something through it. All right, and they'll get you to analyze this situation. So because it's in a thick, dense liquid, there will be drag. So again, what's the resultant force? It's mass times gravity, which is weight minus the drag, and that's going to equal mass times acceleration. If they want to make it even more complicated, what they will do is they'll try and confuse you with some just unnecessary things. So what they'll do is they'll put an object at the bottom. They'll put maybe a pulley here. And they will put a weight on here. And what's going to happen? The mass is going to go down. It's going to accelerate the mass in here up. And they'll ask you to figure out what's going on. Okay, so this then becomes just like last lesson where we're going to be looking at the object. So we'd look at this object and we would say the resultant force is mg minus the tension. And then for this object here, we would say the tension minus the weight equals its mass times its acceleration. All right, so just like we did last lesson, but we've got something moving through some liquid. Now, one extra complication, which I just want to point out because this is sometimes in exam questions and it's useful for you to know what it means, is they will often talk about a ticker timer and using a ticker timer to show acceleration. Okay, what a ticker timer is not something we use very much nowadays, but you basically attach some paper to something that's moving, and then you have a little machine that basically pokes a hole in the paper every so often. Every second, for example. Okay, it might be every half second, it might be every quarter of a second, all right? So what does this do? You end up with a piece of paper that looks like this with some holes in. Okay, and obviously the distance between them increases, but the time that these holes were made are at fixed intervals. So what can you tell about this object? If the ticker timer was moving this way, you can tell that the object is accelerating. If you really haven't got a clue what I'm on about, at some point later on today, just Google ticker timer and just watch a quick video of someone doing a practical, right? And you'll see exactly what I mean. We don't have one in school, but they still do use them in exam questions. All right, last piece of information for this section. What exactly do we mean by terminal velocity? Okay, so this is an object falling at a constant speed when weight equals air resistance. So, quick question for you to do. Now, you don't have to write this down, you can just think it through, but I just want you to think about what is going on in this diagram and think about how you would describe this parachutist's motion at 1, 2, 3, etc. So just think about what's actually happening, think about what's happening in terms of the forces and the acceleration and the speed. I'll just give you 2 minutes to think this through. Okay. Can I please ask Io, if you could please just describe what is happening in the different parts of this graph? We want to know about the forces and the acceleration.
Are you talking about example 2?
The one that is on the screen now. So this graph.
Oh, wow. I haven't seen this. Okay. I was looking at the paper.
Oh, right,
Um,
sorry. Okay.
uh, it looks like the acceleration is increasing like exponentially, and then like from let's say from 1 to 2 is increasing exponentially. Then from 2 to 3 is slowing down. Then from 3 to 4 it stays consistent. Then at 5 it's the it reaches the like almost like peak like acceleration, and then
I'm just going to interrupt you there. What is on the y-axis of this graph?
speed. Oh
Speed.
wait, never mind.
So
Speed
at
up.
1, what is the acceleration?
0.
So what do we mean by acceleration? What's the definition?
Um, Change in velocity over time.
So is the velocity changing at this point?
No.
Are you sure? What's happening to the speed? The speed is increasing quite a lot.
Oh, but at point 1 is 0.
So point 1, the speed is 0, but is the speed changing at point 1?
Oh yeah, it is.
Right. So if this was on a piece of paper in front of you, how would you work out exactly what the acceleration is here?
You did the tangent, right?
Exactly. So the tangent is really steep, so the acceleration is really high.
Oh, okay.
So how does the acceleration compare at number 2? Is it the same, greater, or less?
Oh, it's slowed down, and then at 3 is even slower, and
Well,
at 4 is
we shouldn't say slower, because slower means speed. What's happening to the speed between 1 and 5? It's,
increasing.
yeah, but the acceleration is,
Increasing.
no,
Oh,
what's happening?
decreasing. I mean, sorry, yeah, decreasing, decreasing.
Decreasing. All right, good. So the speed is increasing, but the acceleration is decreasing in each of these cases, right? Because the tangent is getting less. And then at 5, is there any acceleration at all?
No.
No. So at 5, it's reached its terminal velocity.
All
Right,
right.
at 6, what's the acceleration at 6?
Um, it's there's a lot of acceleration.
Correct? Is it, would you want to add any extra detail? So if you compare the
It's
acceleration at
going
6,
in the other direction,
good.
so that would mean that the direction has changed.
Yep, so instead of accelerating downwards, it's accelerating up.
Upwards.
Good. So what do you think's happened at 5?
Um, oh, the parachute was deployed,
Good.
and
And
then
then,
it um it slowed down the speed,
correct.
and it increased the acceleration, but in the other direction.
Good.
And then at 7, I'm guessing that's when the monkey landed. What was that monkey or I don't know. That's when the monkey landed, and then
It's a strange
there's no
looking monkey, but
acceleration.
we'll go with that. So at 7, there is a speed. So the speed is this, whatever that is. So they're
Oh
moving
yeah,
at a constant speed. And then where do they land?
they probably land somewhere like safe, like
Well, sorry, okay. Which number do they land at? They land at number,
oh they land at 8.
yeah, all right, because there's this large force, which is going to be the force from the ground, which slows them down.
All right,
All right, thank you, Aya.
no problem.
All right, who else shall we ask? Naveed. All right, Aya's given us a description of the acceleration. can you talk about the forces? So I want to know about if there is a resultant force and maybe why the resultant force is changing. All right, so Naveed, at number 1, all right, the object or the person is accelerating. So is there a resultant force on the person? Good, all right. And they're accelerating a lot, so is there a large or small resultant force? Good, all right. If we look at 2, what's happened to the size of that resultant force? Decreases. At 3 and 4, it decreases. And then in this section here, which I suppose is between 4 and 5, what is the size of the resultant force? All right, good. At 6, what's the size of the resultant force? So you sure? So at 6, the object is accelerating. Good. And is the resultant force going to be up or down at 6? So we've got in sections 1, there's someone parachuting. So 1, 2, 3, 4, and 5, they're falling down. So the resultant force is down. At 6, the parachute opens and they decelerate. It slows them down. So the resultant force is going to be up because now we've got this large parachute and the person slowing down. And then at 7, is there a resultant force? Good. And then at 8, is there a resultant force? So at 8, what's happening to the speed? Is the speed changing? Yeah, so is there an acceleration? Good, so therefore, is there a resultant force? Good, and is it going to be up or down? Good, all right, the ground is going to provide this upwards force to slow this person or monkey, according to down. All right, and then final question. We have the object or the person is accelerating between 1 to 5. Why is the resultant force decreasing and why is their rate of acceleration decreasing? What is the reason for that? Anyone else? What is the reason for this changing acceleration between 1 and 5?
Resistance.
Bit more detail, Morali.
Drag. Because like there's a parachute.
No, the parachute opens at 5, which means there is this large deceleration.
Wait, no. Oh, maximum velocity. So like you reach maximum speed, so you can't accelerate anymore.
So that is at this point between 4 and 5.
Oh, right.
Between 1 and 4.
Not sure, sir.
So we've got an object. What force is pulling it down? It's the weight. What force is pointing up? It's air resistance or drag. Why will the air resistance increase between 1 and 4? What is causing it to increase?
Oh, an increase in weight.
An increase in what, sorry?
Weight.
What, really? You jump out of a plane and your weight changes?
I'm confused, sir.
So between 1 and 4, the object's speed is increasing, right? We can see the speed increasing.
Yeah.
So, Akira, what you can say?
I'm not sure, but is it because your thrust is... Actually, no, that made no sense. No, forget. I was going to say, is it because your thrust is increasing because you're going faster?
No, because the thrust in this case is the force downwards, which is the weight, and your weight isn't changing. But there is a force up, which is trying to slow you down or stop you accelerating, and that force is air resistance or drag. All right. What happens? Your speed is increasing. What happens to air resistance the faster you go? It increases. The faster you go, the more air resistance there is. I think what we might do is just do a couple of quick notes on this. So if you pin my screen again. So we've got height and we've got speed. And we've got this graph is for a person jumping out of a plane. With a parachute on. So their speed is increasing, then it reaches its terminal velocity, then it decreases very rapidly. We reach a new terminal velocity and go back to 0. So what is happening? They're accelerating. The air resistance increases. The resultant force decreases until terminal velocity. So no resultant force. At this point here, the parachute opens. Okay, and there is a large resultant force up. So there is a large deceleration. Okay, and then we've got a new lower terminal velocity, and then the ground exerts an upwards force to decelerate the person. So this is the diagram of the person. The weight is constant. Right, you can't change your weight when you're in the air. And D is the drag or the air resistance, which increases with speed. So if there's one thing you remember this. Weight is constant, air resistance increases with speed. Right, are there any questions on that? Okay, we'll look at briefly at the other kind of application of F equals MA, how they will make questions harder. And I'm going to set you off on some practice questions. So we're going to look at impact forces and car crashes. So the first bit, this is a bit of GCSE recap, is basically how far will it take a car or a vehicle to stop? All right, this is always the bit of GCSE where people are a bit like, oh, this is really boring, but actually it's quite useful, right? A lot of you probably are going to want to learn to drive in the next couple of years, right? And this is basically on the driving test, right, this part. So how far does it take a car to stop? That's known as the, that's known as the stopping distance. How far does it take it to stop? And the stopping distance is the sum of two things. It's the sum of the braking distance, which is how long it takes you to actually brake, plus thinking distance, which is how long it takes you to think and how far you travel while you are thinking. So when you're thinking, you're still moving at a constant velocity and you're thinking for some time. So the distance that you travel is going to be the velocity times time. When you're braking, you are now decelerating and you obviously brake over a period of time. So what is the velocity? What is the distance that you travel? So we can get it from a Suvat equation. So we can rearrange v squared minus u squared is 2as. And we can rearrange this. So your total stopping distance will be this plus this. Okay. What factors affect this? So this is really kind of common sense. What would affect how long it takes you to think? So your reaction time, things like being tired, if you stayed up all night to watch a Super Bowl.
Drunk.
Yep, Sammy?
Is being drunk on.
Definitely, yeah.
I don't think people really are allowed to drive under the influence anyway.
No, you're not. There's a very, very small limit for alcohol in the UK, but it's not very much. If you were drunk, you certainly wouldn't be able to drive. Drugs equally as well, including caffeine, right, which may actually increase your reaction times a tiny bit, especially if you're tired. Distractions. So if you've got some annoying people in the back of the car screaming and shouting, that's going to increase it. Yep.
It's like the road being like icy or wet. Braking distance or thinking distance?
So does iciness cause you to change your thinking time?
No. But what if you're like, you know, the road's like icy, so you're like, I'm gonna brake early?
So
Or is it just reaction time?
it's just reaction time. So you might be really focusing and really careful and you might be going slower, but actually if somebody runs out in front of you, your reaction time is the same no matter what. Okay. But you're right, the amount of time it takes you to actually brake will be massively increased if it's icy roads or wet roads. Obviously your speed, the mass of the vehicle, the more massive it is, the longer it takes, right? Things like the condition of your brakes or your tires. If you've got old tires or you've got worn brakes, obviously it's going to take you longer to stop. And then other things like road conditions. So if the road was full of like loose gravel, then you might skid, right? If it was brand new tarmac, it's going to be a lot more grippy. And then the final thing that we'll talk about is what would happen if there was a crash. So worst case scenario, you can't stop in time. So how can we model what would happen in a crash? So there's basically three things we'll use, and none of this is new. It's just maybe applying it to a slight new situation. Okay. So the impact force that you would feel is obviously mass times acceleration. The acceleration that you feel is your change in velocity over time. And the other thing that is really useful as well is the impact time is given by this. And if you're not sure where this comes from, this is just u plus v over 2 times by time is s. So this is saying your average velocity times time is your distance. So how can you, what hurts in a crash? Why a crash is dangerous, right? It's because there is a force on you, a force due to your change in velocity. So how can you reduce the force? Well, obviously you could reduce the mass, or you could, go slower. Right? You can't reduce the mass if you're driving, but obviously that would impact it. You can obviously slow down, which you try to by braking. But the main things that are going to affect it is the impact time. So if we look at impact time here, again, what affects it? Well, obviously your speed, but also the distance over which you crash. So how can we increase the impact time? Well, we can do things like put safety features in. We can use things like airbags to slow the crash down, crumple zones on cars to make sure that the front of the car squashes a bit and increases the time of collision, seat belts, there might be things like bumpers on the car, which basically do the same as crumple zones. You might have things like collapsible steering wheels that actually do the same kind of thing almost as an airbag. And obviously, if you were, jumping off a building or something, what would you do to increase your impact time? You obviously would bend your knees. Right? So it does exactly the same thing. It increases the time, decreases the force.